Good morning. My project is about mixed interlinear programming and how it can be used to solve allocation problems, specifically a hospital allocation problem. Okay, so first we're going to look at the research question. Then we're going to see how MILP can be used to solve for this question. Then we're also going to take a look at the technical aspects of this project, such as the constants, variables, constraints, and objective function written in the code. Then we're going to take a look at the results and how this project can be further extended and improved. So first of all, this research is a healthcare optimization problem, and solving this can aid in raising the quality of healthcare and also improve resource allocation. Examples of optimization are vaccine distributions, efficient deployment of human resources, and cost-effective delivery of services. In particular, the research question is, given M cities with specific locations, where are the optimal sites to build hospitals, which reduces the total building cost and minimizes the sum of the distances between each city and the closest hospital? Okay. So to solve for this problem, we have to first take into consideration the cost of building hospitals, and then we also have to see the distance between the various cities. Since this problem is NP-hard, we're going to use mixed interlinear programming to solve for it. NP-hard problems are problems which are difficult to solve, and therefore there's no predefined algorithm which can find an optimal solution. And even when you find a solution, it is difficult to prove that the solution which you found is the actual optimal one. Talking more about MILP, MILP is a type of optimization problem. And in general, optimization problems, you have to define the variables, constraints, and an objective function. Specifically, in MILP, the variables are integers and the constraints are preferably linear. MILP was coded using a programming language called Gioia, which has a fast execution time and is also easy to use. Finally, a folder in Gioia called jump was used to solve this mathematical optimization problem. So as it can be seen, in optimization problems, the variables are usually continuous, and also the decisions are continuous. On the other hand, as stated before, in MILP, the variables are integers, and the decisions are usually discrete. And MILP is also useful in solving difficult NP-hard problems. Now let us look at the technical aspects of this project. M represents the number of cities which will be taken into consideration in the code, and this will be a predefined constant. Furthermore, it is also important to note that cities do not have to refer to physical cities, but can also refer to clusters of population. Then we have to give each city a specific location, and this will be done using PI. PI has two coordinates, an X coordinate and a Y coordinate, and these two coordinates will be randomly generated by the code and are constants on an arbitrary scale. Then CI will be the cost of building each hospital, and also the cost will be randomly generated, and there will be a minimum and maximum value which the cost can have. Finally, Dij will simply be the distance between the various cities. Next, the optimizer has to solve for some variables, and in our case we need two variables, xi and yij. In MILP, the variables are usually integers. And furthermore, in our problem, we would like our variables to be Boolean, because this makes the problem easier to solve. So xi will be the Boolean variable, which represents if there's a hospital in city I, and yij will be the other Boolean variable, which represents if hospital in city I is serving city j. And as you can see, this is how we write the variables in the jump code. So since they're variables, we write at the variable in the beginning, and then there's a need to define the model, and x and y are going to be the names of the two variables. And since they are arrays, we're going to be writing the first element and the last element of the array inside the brackets. And finally, they're binary, so we're going to simply write bin. Next, in this problem, there was a need to define two constraints. The first constraint says that each city has to be served by exactly one hospital, and there are going to be m of these constraints, one for each city. The mathematical equation used to represent this is the sum over I from 1 to m of yij equals to 1 for j from 1 to m. This equation holds true because for each city, we would only like one combination of city hospital to be connected. And as the constraint says that each city should be served by exactly one hospital. And all the other pairs of that city hospital should be equal to 0. Therefore, when summing up all of the pairs, it should simply be equal to 1. Again, you can write the constraints in the jump code by writing add constraint, defining the model, and then simply by writing the mathematical equation using the various symbols. The second constraint says that city I can only serve city j if a hospital has been built in city I. And there are m squared of these constraints for each hospital-city pair. The mathematical equation used to represent this is yij less than or equal to xi. And this holds true because when xi equals to 0, this means that a hospital has not been built. And as it can be seen from the equation, yij, since it's less than or equal to xi, can only be equal to 0. So a hospital which has not been built cannot serve a city. Meanwhile, if xi equals to 1, then yij can be either 0 or 1. Therefore, based on the cost and the distance, the code can decide whether that hospital which has been built should serve one city or if it should serve another city. Again, this is how we write the constraint in the jump code. And one might be wondering, don't we need an additional constraint which says that a city should be served by the closest hospital? And in this case, we do not need this additional constraint due to the fact that this problem is convex, meaning that when the optimizer tries to find a minimum value, it will automatically go to the global minimum. Therefore, it will automatically try to find a hospital which is the closest to a city. Therefore, since this problem is convex, the requirement that a city is served by the closest hospital is automatically satisfied. Finally, let us look at the objective function. So in the objective function, the objective function is important in optimization problems as it is the function that the solver either has to minimize or maximize. And in our case, we would like the solver to minimize our objective function. And in it, we would like to put two requirements. The first requirement being that we would like to improve accessibility by increasing the number of hospitals. At the same time, we also want to minimize the total cost of building hospitals, therefore reducing the number of hospitals at the same time. And these two requirements compete with each other because in the first case, we would like to increase the hospitals, decreasing the distance between each city and hospital. And in the second requirement, we would also like to minimize the number of hospitals, causing an increase in the distance between each city and hospital. Therefore, the optimizer has to find an optimal value somewhere in between these two requirements, which can minimize the objective function. When writing this objective function, one might try a naive approach, and that is to simply sum the two terms together as they are. However, this does not produce a realistic result because the two terms are not homogeneous, and as it is the case in this problem, they have different scales. For instance, CI could be millions of pounds, and DIJ could just be hundreds of kilometers. Therefore, the optimizer might give more importance to either the cost or the distance, without giving equal importance to both terms. As it can be seen here, when the solver tries to solve for the problem in which the objective function has different scales, in the example on the left, one can see that only one hospital got built because the first constraint scale, the cost, weighed much more than the second constraint, the distance. Therefore, the solver just tried to minimize as many hospitals as possible. And in the example on the right, too many hospitals got built due to the fact that the second constraint scale, the distance, weighed much more than the first constraint, the cost. Therefore, the optimizer just tried to minimize the distance between each city and hospital and built many hospitals. This research proposes a solution to this problem, and that is to divide each cost and distance by the maximum cost and maximum distance respectively. In this way, the two terms become pure numbers and they become homogeneous. Therefore, since they also become comparable in scale, they contribute similarly and equally to the code, and the optimizer can find a realistic solution. Again, this is how the objective function can be written in the jump code. So we write add objective, we define the model, and then since this is the solver is trying to minimize the objective function, we write min for min, and then we simply write the mathematical equation as it is. So this is one of the results which the optimizer solves for when the objective function is normalized, and the two terms have similar scales. So as can be seen, this is much more realistic than the previous two images. The cities are divided into groups, clusters, and based on the cost and the distance, each hospital can serve 1, 2 cities, or even more than 10 cities. To conclude, this research proves that MILP can be used to solve this NP-hard optimization problem, specifically hospital allocation problem. And one way we can extend this research is, for instance, to consider hospitals of different sizes, different services, and hospitals with different capacities. In this project, we used mock data. However, in real life, it would be obviously better to use real data instead. For instance, we could also consider transportation feasibility, therefore how easy it is to get from a hospital to a city. And we could also divide the population into age groups and optimize hospital services based on each age group. Finally, in this research, we only considered building hospitals in cities, but it might be better if we could also consider building hospitals outside of cities, for instance, in rural areas as well. Before finishing, I would like to thank Dr. Benoit Lega for helping me throughout this research project. I would also like to thank the TAs for teaching me so much about optimization and MLP. And finally, thank you to CCIR for giving me the opportunity to write and present this project. Thank you for listening.
Thank you so much for your excellent presentation. It happens to be the core area of my PhD, so I don't want to hog up any questions. Leave the first questions to the audience. Any questions? Unfortunately, it comes to me. So the first question, maybe general question is, why Gioia? Maybe to someone who codes here, we prefer Java, C++, Python. Do you have any specific reasons?
Yeah, basically, so for example, in Python, you can use it to code maybe simple but also difficult programs, but it might take lots of time for the Python to solve it. Meanwhile, in Gioia, it has a really fast execution time, so you can give it many complex problems and it can solve it really quickly. And moreover, also the formatting, Gioia was actually made in a way such that it is easy for even beginners to use it. Therefore, you can literally just read the code and understand what is written. Meanwhile, in Python, it might be maybe a bit difficult. Maybe you don't know the meaning of some of the, elements written there. Yeah.
Thank you. Just one follow-up question. Do you know what are some other available methods to solve the same question?
So I guess you could use so I used MILP in my research, which is specifically used to solve NP-hard difficult problems. However, I guess you could use general optimization techniques, but you would have to give the code more constants, more constraints, and by giving it more stuff, it would just make the time to solve it really long and make it just more complex. So, yeah.
Thank you so much. Let's start our